Hello friends, continuing with the topic electric dipole in uniform electric field. Today we derive an expression for potential energy of electric dipole free to rotate about an axis passing through its midpoint perpendicular to its axis when placed in uniform electric field. Now introduction. An electric dipole free to rotate about an axis passing through its midpoint perpendicular to its axis when placed in uniform electric field and is inclined at an angle theta with the field possess potential energy U equal to minus P dot E. I repeat, an electric dipole free to rotate about an axis passing through its midpoint perpendicular to its axis when placed in uniform electric field inclined at an angle theta with field possess potential energy U equal to minus P dot E. Now let us develop a physical situation. Now consider an electric dipole consisting of two charges plus minus Q. This is plus Q, this is minus Q. Separated by a small distance 2a such that its electric dipole moment P is equal to Q into 2a. Mark it as equation 1. Let the dipole, which is free to rotate about an axis passing through its midpoint perpendicular to its axis, be placed in uniform electric field inclined at an angle theta with the field. Angle theta is angle theta and this is field inclined at an angle theta with the field as shown in diagram. Then the electric dipole experiences a torque. What happens then? Electric dipole experiences a torque tau equal to P cross E or equal to mod P mod E sin theta. Let us mark it as equation number 2. Now in the diagram you can see red arrow is the electric dipole and cross within blue circle, that is the midpoint of the dipole through which axis of rotation pass, where that is perpendicular to dipole axis, and the dipole is inclined at an angle theta with the field. So this is the diagram. You can understand in this situation the dipole experiences a torque tau equal to P cross E. Let the dipole be rotated through a small angle d theta against the torque. Then small work done dW is equal to tau into d theta is equal to mod P mod E sin theta d theta. Mark it as equation 3. I repeat, let the dipole be rotated through small angle d theta against the torque. Then small work done dW is equal to tau into d theta and it is equal to mod P mod E sin theta d theta, because torque is equal to mod P mod E sin theta. So we have marked it as equation number 3. Now total work done W, that is equal to U. U is for potential energy and W is for work done. Now we have to calculate total work done in rotating the dipole from the initial position theta equal to 0 to final position theta equal to theta. Okay, so in the diagram you can see the dipole is rotated through small angle d theta against the torque. Okay, and this is the midpoint of the dipole through which axis of rotation pass, and that axis of rotation is perpendicular to dipole axis, and this is electric field. Okay, so dipole is free to rotate about this axis passing through its midpoint perpendicular to dipole axis, and is placed in uniform electric field of strength E. So in this situation we are to calculate now total work done W and is equal to U in rotating the dipole from 0 to theta. Okay, now total work done in rotating the dipole through an angle theta can be obtained by integrating equation 3. Now let us integrate equation 3. Now integrating equation 3, we have integration dw is equal to integration tau d theta, or it is equal to 0 to theta mod p mod e sin theta d theta, or it is equal to pe minus cos theta limit 0 to theta, or it is equal to minus pe cos theta, and it is equal to minus p dot e, or we can write w is equal to minus p dot e. Let us mark it as equation 4. Now minus sign shows that work done is negative and is stored into the system in the form of electrical potential energy, or we can write equation 4 as u equal to minus p dot e, or we can write it as u is equal to mod p mod e cos pi minus theta. Let us mark it as equation number 5. Now we come to discussion part of it. Now since or consider equation 5, u equal to mod p mod e cos pi minus theta. When theta is 0, p is parallel to E and u will be equal to minus p e, maximum negative. Okay, because cos when theta is 0, u will be equal to mod p mod e cos pi, and cos pi is minus 1, so it will be equal to minus p e and maximum negative. Electric dipole is in stable equilibrium. So when theta is 0, potential energy is minus p into E, maximum negative, and electric dipole is in stable equilibrium. Now second point, when theta is 90 degree, then P is perpendicular to E, and then U is equal to mod P mod E cos 180 minus 90 will be equal to mod P mod E cos 90, and cos 90 is 0, so potential energy will be equal to 0 minimum. So total work done in bringing a dipole into the field is 0. Now third point, when theta is 180, P is anti-parallel to E and U is equal to mod P mod E maximum and is positive. Electric dipole is in unstable equilibrium. Okay. Now I sum up. When theta is 0, potential energy is minus P into E, maximum negative. Electric dipole is in stable equilibrium. When theta is 90 degree, P is perpendicular to E, potential energy is 0 minimum. Total work done in bringing a dipole into field is 0. Third, when theta is 180 degree, P is anti-parallel to E and U is equal to P into E, maximum positive, and the electric dipole is in unstable equilibrium. And that's why while rotating a dipole from theta equal to 0 to theta equal to 180 position, the potential energy is twice Pe. The work done is twice Pe, and the dipole is in unstable equilibrium. Now assignment 4 1.4 continued. Assignment 1.4 continued. Now assignment 1.4 continued. Question number 12. An HCl molecule has dipole moment of 3.4 into 10 raised to power minus 30 coulomb meter. A sample contains 10 raised to power 21 such molecules whose dipole moments are all oriented in the direction of the field of 2.5 into 10 raised to power 5 newtons per coulomb. How much work is required to rotate the dipoles from orientation theta equal to 0 to the one in which all the moments are perpendicular to the field? So here is the answer. How much is the total work done? 8.5 into 10 raised to power minus 4 joules. Now question number 13. Calculate the total work done in rotating the dipole through an angle of pi radians, and total work done will be equal to 2 into P into E, twice PE. Question number 14. Whether the dipole is in stable or unstable equilibrium when number 1 theta equal to 0 and number 2 theta equal to pi. So you answer these questions on the basis of the text that you have learnt. Okay, with this we finish the topic of electric dipole. Next time we will start with the topic of electric flux. Okay, thank you so much. God bless you.